Welcome to Lecture 16 of Finite State Machines. This is the second part of finite state machines, and what we'll be looking at today is Moore and Mealy finite state machines. So we'll do an example where we compare the two and look at some of the advantages of using a Mealy state machine. And then finally we'll do something that's quite important, especially for the exam, is where we'll start with a schematic diagram and then derive from this schematic diagram, reverse engineer it to figure out what the state machine actually does. So we'll do the opposite of what we've been doing up to now with state machines. Right, so in the previous lecture we said you get Mealy and Moore state machines, and the Mealy state machines are ones in which the output is directly dependent on the input and not only on the current state or the present state. For the Moore state machines, the output is only dependent on what the current state is. So you'll recall that from the previous one. But how we draw these state machines also differ. The way in which they differ is as follows. For a Moore state machine, we draw the states, we give each one of them a label or a name, and then we have inside, we specify what is the output in that state, because the output is dependent on the state. And we also indicate here transitions, and that transition can happen on a clock, which means we don't put anything here, or it can be dependent on an input at a clock edge, and then we put the input here. That's for a Moore state machine. For a Mealy state machine, for the Mealy state machine, we have the states again, but now the state does not have an output. Now the output depends on the input and the state. So it transitions from a state based on an input, and the output also changes as we have the input. So the output changes immediately when the input changes, and that input causes a transition. It might actually not cause a transition. So in this case you can see, let's say we entered into this state from this path here. The output was 1, the input was 1. It's in this state, and then it has an input of 1, and now the output changes to 0. So you can't tell what the output is by looking at the state. You can only tell what the output is by looking at the transition which was driven or caused by an input in combination with the original state that it came from. Okay, that's a mouthful. It'll all make sense when we look at the example that we have. So this example is quite nasty. It involves snails smiling, and it really describes something that's a bit more generic and actually quite useful. It describes a sequence detector. So let's call it a sequence detector, and let's leave the snails for the French. This sequence detector works in the following way. There is a certain sequence of input values that needs to be detected by our circuit. And in this case, the sequence that we're looking for is the sequence 0, 1. So there's an input. This input value changes 0, 1, 1, 0, whatever. And then we want to detect the sequence of 0, 1. Whenever we have the sequence 0, 1, we want the output to be equal to 1. In all other cases, we want the output to be 0. So this is a very simplistic sequence detector. Typically you're looking for more a longer sequence, which means you need more states to do it. But in this case we're just looking for 2 bits. So now we can do it in 2 ways. We can either do it with a Moore state machine or a Mealy state machine. If you're using a Moore state machine, then this is the way that we're going to do it. We're going to say, let's define a state S0. When there's a reset, we enter the state, which means this state is also the state in which we've received no part of that sequence yet. All we've received is either nothing because the power has just cycled, or we've received a 1, meaning that the sequence that we're looking for, we've not managed to get any of it. We've only received a 1, so we've not received that 0 of the 0, 1. If we then receive a 0, or if the input is made 0, then we go into a state S1, which might have been called I've received 1 bit of the sequence I'm looking for, but that's a long name. In that sequence, or in that state I should say, we've not received the 0, 1 yet. We've only received the 0, which means the output is still 0. Obviously here it's also 0. If we get another 0, we're in the same position. Of that whole sequence we're looking for, we've only checked 1 bit. If we're in this state and we receive a 1, then we go into a position where we can say with confidence the last two inputs were 0, 1 or 0, 1. Whichever way, we've received a 0 and a 1, which is fantastic because that's what we're looking for. We want to put a 1 in here. That's the output we're looking for. In this state, we could then receive a 0, which means we're back here where we received one of the bits we're looking for, or we receive a 1, which means we're out in the cold, we haven't received any of the bits we're looking for. And this is the state machine as you would have done it with the Moore state machine. Now let's consider the Mealy state machine, which I find a bit more difficult to design with, but it's usually a bit more efficient. It uses less flip-flops, and often, as you'll see in a second, it also gives a faster output. In this state machine, we start again by saying this state is my starting state, so it's the it's the reset state, and then we say this is also the state in which the last thing we received is a 1. The last thing we received is a 1. So either we received a 1 and the input is 0, or we received a 1 and the input is 1. Don't worry about that for a moment, we get there now. If this is the state in which we are, if the last bit we received is a 1, this state, we're going to make the state in which the last bit we received was a 0. So let's start here. We've received a 1. This is the reset state. Because we're looking for a 0, 1, we make this also the state in which the last thing we received is a 1. So we've not received any valid bits. If we receive a 0, we make the output 0 regardless of what it was. Output 0. And as it enters this state, the last thing we've now received is a 0, but the output is still 0. Then, if we receive another 0, we're in this condition again. So the last thing we received is a 0, and the output stays 0. If we transition from here, and we receive a 1, the output needs to be made 1 as well. That output goes to 1 immediately when this input value changes, and then the straight transition happens only on the clock cycle. So the output changes immediately, and that state change happens on the clock cycle. But the output stays 1. It stays 1 in the state if it came from there. If we receive a 0 then, it jumps back to here, but the output is 0 because we've only received a 0 in that sequence. If we receive another 1, so after we've transitioned from here we get another 1, then the output must be 0. So we've received a 1 and another 1, which means not the sequence we're looking for, output equal to 0. And that's the whole state. So this is our state machine. That is pretty impressive. So a Mealy state machine can do it in 2 states, where the one is a conceptual, I have received, the last thing I received is a 1, the last thing I received is a 0. This one here was more like, I'm looking for a sequence and I'm going to make one bit of that sequence represent a state, or a state represent one bit of that sequence. This one is a bit more conceptual and abstract, saying let's make a state for whatever we received last. Right, so how do we take this further? So now we need to put this into our state transition tables. So the state transition tables, as you can see here, it's pretty obvious. For state 0, we're either going to receive a 0 or a 1. This is the Moore state machine, by the way. This is the Mealy. And then it needs to go into state 1 if I receive a 0. That's the first bit that I'm looking for. If it gets a 1, it means no, I've not received anything I'm looking for, so it's an S0, stay in that state. From S1, we either stay in S1 if we get another 0, so I've just received one bit of the sequence I'm looking for, or if it receives a 1, it means, hey, I've received a 0 and a 1, so it goes into S2. And the same for S2 then, if it receives a 0, it goes to S1, S2 it receives a 1, it goes to S0. And then we also have to do the output states. So in state 0, 1, and 2, the outputs are 0, 0, and 1 respectively. Now for the Mealy one. The Mealy one is subtly different. These transitions obviously happen on clock cycles, on a clock edge. these output changes happens as it enters into these states on a clock edge. They're clocked through using the flip-flop. On this side, it's not the same. On this side, we're saying if this is the current state and this is the output, this is the input, I should say, then the output must be that immediately. It doesn't wait for the clock. However, the next state change, that does wait for the clock. All right, so there's a subtle difference implied in these tables that you can't see by just looking at it. But what you can also very clearly see is there's a one-to-one relationship, actually a one-to-one, yeah, there's a direct relationship between the states and the outputs. In this case, one state can give two different outputs. So there's not a direct link because the inputs also affect it. So this is the state from whence it came and the current input, the stem state, current state, and the input gives you this output. This is how you're supposed to read it. And when there's a clock edge, this will be the next state. What you do then is you take these and you just give them numbers. So each one of them you just give a number. And in this case, the current state S0, we made state 0 because that's where the reset originated. So if it resets, it goes into state 0. This is state 1 and this is state 2. We don't have a state 3, so there's a few stuff implied here. Obviously, these are the inputs that lead to the next state. So this is just rewriting the codes instead of the names. And then for each one of those states, they have specific outputs. So this is just rewriting these. Instead of S0 and S1 and S2, we're just writing 0, 0, 0, 1, and 1, 0, just coding it. In this case, for the Mealy state machine, we only have two states, which means in this one we needed 2 bits to represent the state. In this one, we just need 1 bit to represent the state. So our current state, S0, represents everything. So either in state 0 or in state 1, and we have an input, which is 0 or 1. So this is a much easier truth table to work with. And that's it. And for the output, you just code those as well. Now getting to the circuit. So now we have to design these two. So this one here is again Moore, that's Mealy. So if you were to do the truth table for this, and you included all the don't cares and everything, and you were to derive this logic here, you'll end up with not S1, so the next state's most significant bit is just equal to the current state least significant bit, and it with A. And the least significant bit of the next state is just equal to not A. That's what you get when you just calculate those here. And this is what it will look like. So you've got the flip-flop, which is the register containing 2 bits, the 2-bit flip-flop. And it has a most significant bit, least significant bit. This one is equal to the and there, this one is equal to the not there. And then the output, which is directly dependent on the output of my flip-flops. And in this case, it's just equal to S1. If you look at this, S1 directly drives the output Y. Okay, for the Mealy state machine, it's actually looks simpler, but it's not much simpler. So in this case, you can see the next state here is equal to not of A. The next state is equal to just that, nothing else, which means the next state does not depend on the current state. And if you just flick back here, that's what we said. This just says, what did I receive last? It doesn't say anything about the previous state. It just says, what did I receive last? So the next state is just dependent on what did I receive last. The output, however, is dependent on what is the input and what is the last state. So if I received a 0 last and now I received a 1, the output will be 1. If I were to draw that out, that's just not A driving the state's next state, the state machine's next state, and the output is just equal to the AND of A and this S0, the state bit. So whenever A changes, Y will change immediately, which brings us to the timing diagram. So I'm not going to go into too much detail. The only thing I want you to pay attention, you can work through this on your own. What I want you to pay attention to is A changes, but it does not affect the state of the Moore state machine. This is the Moore state machine. Its state only changes here when there's a rising edge and A changed. However, the Mealy state machine, because of this here, direct link, its output y changes immediately when A changed. So this here drove that change there. And this state is then the state transition that happens afterwards. So that's important to understand. Another thing to just appreciate is this Mealy state machine, because it changes immediately, it doesn't wait for that state to ripple through, the output changes a clock cycle earlier than the Moore state machine's output changed. So that's one of the benefits of a Mealy state machine. The other one is obviously often it uses fewer components. In this case, it uses one less flip-flop to perform its duty. Now we get to a totally new topic, so just park all of that. Now we're going to go in the opposite direction. So now we're giving you a circuit and we ask you, what is the state machine that sits behind the circuit and what does it do? So the process is exactly the opposite. We start with a circuit, so we examine the circuit, and what we then do is we write down the equations, then we create the state tables, then we change those numbers in the state tables to, at least we change the tables to throw away all the unnecessary states or all the don't care conditions or the illegal states. Then we capture names, so we just give monikers or names to the states rather than just the coded numbers. Then we rewrite the states tables with, at least we rewrite it with those state names, draw the state diagram, and then state in words what the state machine does. So we're going to do an example now which will illustrate this very clearly. We end up by analyzing this state machine that we described in words by saying, okay, so what does that mean? What does this actually do? What is the function that this thing performs? So here's another example from the same snail lady as before. And this time she's lost the key to her house. She doesn't know how to get in. So she has a PIN code that she needs to enter into a keypad, and she forgot this. But she has the circuit. So now she's going to analyze the circuit to determine what is the PIN code that she needs to get into her house. So this is the circuit that we receive, and what we can see clearly is here's a flip-flop. That looks like an output. This looks like next state logic. It is a Moore state machine because there's no direct link between the inputs and the outputs. And all we have to do is figure out what is the right code to get into this system. So firstly, as I said, we see that it's a Moore state machine. What we then do is we calculate the equations. So the equations of that next state most significant bit we can read off. It's just equal to A0 and it with not A1 and it with S0, which is the present state or the current state's least significant bit, and that's this. Do the same for S0. This is S0, the next state's least significant bit. That is the AND of the not of S0, the not of S1, and A1 and A0. So that's the logic there. And then finally, the output in this case, there's no logic here, it's just a piece of copper, meaning it's just equal to S1. Right, so now we've got these formulas. Let's now populate the tables. So these are the formulas just duplicated. And as you can see, this is just a normal Carnot map with inputs to the combinational logic block and outputs. Now, a few things will happen here that are not intuitive, so just pay attention real quick. Firstly, you can see that this is essentially state 0, this is essentially state 1, this is essentially state 2, and this is state 3. Okay? Some strange things to note. Here in stage 2, or state 2, I should say, there's nothing, oh, that's a bit skew, sorry, there we go. Here in state 2, this does not matter, it always ends in state 0. So this is one big don't care condition. If it's ever in state 2, it reverts to state 0. So that's an important thing to understand. So these will be don't cares. Another important thing to note is, although this is a state 3, there's no way for the state machine to enter into state 3, which means state 3 is an illegal state. No input condition whatsoever leads to a state 3. There's no way to get into it, which means this is one big don't care condition. We don't care. So that's important to note. The other thing that we write down is just the output truth table, and as you can see, the unlock is equal to the most significant bit of S1, which means if S1 is 1, it goes into unlock. But importantly, we've just said this does not exist. It's an illegal state, which means this row here also turns into a don't care condition. So if we take away that state 3, and if we include those don't cares in state 2, this is what we're left with. And we're going to do that in a second, but what I want you to just notice real quick is this is state 0, this is state 1, and this is state 2. Okay, so just keep that in mind. State 0 can go into either 0 or state 1. State 1 can go either into state 0 or in state 2. And state 2 will always go into state 0. So already we're getting an idea of where this is going. In terms of the output, we've just thrown away state 3 output because it doesn't matter, it's don't cares. Now we're going to do, we're going to convert these 0, 0, 0, 1 and 1, 0 of the states. We're just going to give it names. So we're going to say this is S0, this is S1, this is S2, and the same here. So that's all we do here. We just give it names. And these names, as you can see, now start to make sense. The other thing that we do, is we change this into just a normal number. So this is 0, this is 1, this is 2, this is 3, this is 0, 1, 2, 3, and this is don't care. Because in our problem statement, we said she enters a number, and that number was binary coded. Okay, so if you consider that, what this is saying is the reset state means nothing has been entered. If we then enter a 3, it goes into state 1. Otherwise, it just stays there. So state 0, if we enter a 3, it goes into state 1, or it just stays there. If we're in state 2 and we enter a 1, it goes into state 2. Anything else will just go back to state 0. So if a is not equal to 1, it goes back to 0. And then if it's in state 2, it always goes back to state 0. Okay, cool. What in terms of the key, the output? The unlocking function, as we said, is only active in state 2. So in order to unlock this key, the states are enter a 3, enter a 1, and unlock. And you're in. So there we've gone and derived the state diagram from a schematic circuit. So in the next lecture, what we'll do is we'll be looking at arithmetic circuits. So we'll look at how to develop your own adder, which is essentially a state machine, how to do a subtractor, which is basically an adder with a few 2's complement magic around it, and then we'll be looking at how to do comparators. Thanks.